This is a fun video because it's a little bit more complicated than the homogeneous case, but not that much more complicated. And we're going to see more of the relationships between different solutions. So it's not quite the same, but it's pretty similar, honestly. So let's look at the linearity principle for non-homogeneous. Wrong principle. What would my elementary school teacher say? All right, so consider now two problems. We're going to consider the non-homogeneous differential equation, dy dt, it'll still be linear, equals a of t times y plus b of t. And its associated homogeneous equation, which will look almost the same. And for laziness, let's call this the non-homogeneous. What would my English teacher say? Non-homogeneous. This will be the homogeneous. So we're going to look at two differential equations, and this is very common. When you're working with non-homogeneous differential equations, a lot of times you will start by looking at the homogeneous version of it, where, okay, what if we didn't have that pesky little b of t at the end? All right, so what would happen? And the answer is a lot of nice things would happen. Don't forget to draw your y here. Okay, that's very important. Otherwise, we have a very simple differential equation. Okay, so this is the problem that we're considering, and we're going to be saying a couple things. I'm writing too big. This principle is not even going to fit on one slide. So it's going to say two things, and we'll talk about these two things, but we're also just going to give a big summary at the end. So specifically, if y sub h of t solves the homogeneous version, and if y sub p solves the non-homogeneous version, then if you add them together, it also solves the non-homogeneous. So that's pretty powerful, right? If you have a particular solution, if you have any solution to this non-homogeneous equation, and any solution to this homogeneous differential equation, then if you add those solutions together, you get a new solution of the non-homogeneous differential equation. We'll see more of why that's powerful later. And again, because of what we know about solutions to linear or homogeneous ones, right? This is the same as saying k times yh plus yp is a solution, right? And the second thing is that, again, with similar notation, if yp and yq both solve the non-homogeneous, so if we have two particular solutions to the non-homogeneous differential equation, then yp minus yq also solves the homogeneous. So we can take one of each to get a solution for the non-homogeneous, and we can take two from the non-homogeneous to solve the homogeneous. So the main conclusion, the very important takeaway, right, is that the general solution of the non-homogeneous differential equation is k times y sub h plus y sub p. That's the general solution to a non-homogeneous linear differential equation from the linearity principle. And it's really a combination of 1 and 2, right? 1 says that this will solve the non-homogeneous, and number 2 says essentially that this is actually all the solutions. Because if you have two non-homogeneous solutions, it solves the homogeneous. And since it solves the homogeneous, that must mean it's k times y sub h. All right, if this solves homogeneous, and we know all homogeneous look like this, then this is equal to k y sub h. We combine these two things and say, oh, we get all non-homogeneous solutions with this formatting, which is really nice. So again, we only have to find one particular solution. And then we found, or we also need the homogeneous solution, but that's usually much easier than the non-homogeneous solution. And then we can get the general solution looking this way, which is pretty powerful. So let us see that in action with an example. We'll save ourselves a little work. Hopefully this example looks a little familiar. dy dt is equal to cosine of t times y plus 1/5 times 1 minus t cosine of t. And again, I like to make these remarks to review some definitions, right? This is first order. It's not autonomous because there are t's in it, but it is linear because, right, this is our a of t, and this is our b of t. Nothing funny is happening to the y. It's not being squared or signed or exponentiated, right? It's a linear, non-homogeneous differential equation, first order. Ordinary differential equation too, because there's no partial derivatives. Okay, well, too many definitions in this class, right? All right, so we already found from before, right? We already solved this one. This was in the last video. So we already know a solution to the to the homogeneous differential equation. We already found that in the last video. That was just k e to the sine t. All right, and we plotted, oh dear, right? We plotted all the solutions for that homogeneous differential equation with a slope field. That's what the homogeneous solutions look like. Now, how do we find a particular solution? And the short answer is we're not going to talk about that yet. We'll talk about it very soon, but not in this video, okay? So in the meantime, suppose I tell you, oh no, I just lost my notes. October, please. Suppose I tell you that we have a particular solution that is just a really nice solution, t over 5. We could verify this is true. The derivative of this with respect to t is 1/5. So the left-hand side is equal to 1/5. And if you plug this in for y, t over 5, and simplify, things will cancel and you will also get 1/5. It is a solution. All right, so we know this is a solution to the non-homogeneous differential equation. Well, the linearity principle says that the general solution is just going to be k times a homogeneous, or in other words, the general homogeneous solution, plus that particular solution. So our conclusion is that the general solution of this non-homogeneous differential equation is just y of t equals the homogeneous solution plus our particular solution. And again, there were many, many particular solutions we could have found. It doesn't matter because no matter what they are, this is going to encompass all of them, which is kind of nuts if you think about it. All right. So this is our general solution, and we can see that. And what's interesting, right, is you can really see this linearity thing happening. What do you think the slope field is going to look like for this non-homogeneous differential equation? So here is the slope field for the homogeneous version. For the non-homogeneous version, right, that was, again, I'm just going to use x here to save myself some time. That was cosine of x times y plus 1/5 times 1 minus x times cosine of y. This is the non-homogeneous version. It looks pretty similar, right? Let's zoom out a little bit to see what's happening. Let's go from -10 to 10, -10 to 10. And let's do that on both. All right. So we can see the periodic nature of the homogeneous solution, right? For the non-homogeneous, let's look at the same bounds. -10 to 10, -10 to 10. And we're going to see something very similar, right? It has a lot of similarities. But what's happening is essentially, wait, did I, maybe make sure I typed this in right. This is cosine of x times y, and this is cosine of x times y plus a fifth times 1 minus, oh, that's y. Okay, great. This should be x. I was like, this doesn't look like this is not making the point I'm trying to make. That's why there's a mistake. Okay, this is making the point I'm trying to make. Now we compare these two solutions. All right. Notice what's happening is, again, I think, make sure that we're in here. What's happening is that it's basically the same solution, but it's kind of tilted a little bit, right? Because we're adding that t over 5 to our solution. We're adding a linear term. Okay? That's kind of fun. Right, we see these similarities, all the similar stuff is getting tilted a little bit. And like, it is getting zoomed out. I'm not actually sure it's supposed to be getting zoomed out, but I guess it is. All right. Yeah, interesting. So yeah, fun stuff. We'll talk more about this in the next video. And again, in the next video, we will also talk about where does this come from? Anyway, until next time, bye-bye.